afternoon session. So this afternoon session we will begin with Gerónimo Uribe. Gerónimo is a researcher here at the Instituto of Matemáticas, and he graduated in actuarial sciences, and after that he made his PhD, of course, graduated in 2007. And the advisors were María Emilia Caballero and Jean Berton. And after, because of this PhD, he received the Weizmann Prize here in Mexico, the best PhD thesis in science. After that, he had like a postdoctoral position in the Institute of Mathematics and Applied Mathematics and System here in Mexico, and also University of California, Berkeley. And since 2011, he joined the Instituto of Matemáticas here at UNAM, and he's one of the main specialists in probability and stochastic processes here at the Institute, and especially in Lévy processes and branching processes, stochastic calculus. So today he's going to talk about random trees and Lévy type processes. So Gerónimo, please welcome.
Thank you very much for the introduction and the invitation. I must say that I'm absolutely honored to be able to give this talk. So I've only been around at the Institute for like 15 of its 75 years, and that's if you count all the PhD work, right? So I've only been hired since about 6 years ago. And, well, you know, most days when I come to work, all I really want to do is, you know, to make this institute thrive so that we can, you know, inherit it with pride to the next generation. So I'm going to talk about inheritance, generations, because that's very suggestive of genealogies, genealogical trees. So I'll be talking about some particular models of random trees. So you can think of them as random genealogical trees. They will be linked to population dynamics and some random functions that one can associate to these random trees, which are of, they're called, the technical name is Lévy process. So here on the picture on the left, you have one of the examples of a random tree. So this is an instance of a random tree. So I threw a bunch of dice this morning and got that tree. If I threw them again, I'd get a different tree. And on the right, you have the picture of what would be a Lévy type process. So this is actually an exact Lévy process. It's called a stable process. And well, as you can see, it seems to be discontinuous, right? In fact, one can prove that in all instances of this random function, the set of times at which this process has discontinuities is actually dense. So this is kind of a very complicated random function, one that we have to deal with because in probability they just appear all the time. Good. So let's start with some history, and that's going back to the year 1875, in which it was still the Victorian era in England, and they were very worried about the propensity to disappear of aristocratic family names. Well, so Galton, a polymath, proposed the problem of mathematically studying the probability of extinction of families. And then Reverend Watson, together with Galton, made this analysis that we still teach to undergrads these days. So what is the model that they were considering? Well, we're going to start, say, with a bunch of initial individuals. Here I started just with one. And these individuals will reproduce randomly, right? So each individual will decide if, for example, it reproduces or not. So this one decided to reproduce, and so the population did not become extinct. So in this particular case, I'm thinking of only binary reproduction. So individuals have either 2 or 0 offspring. You can think of, throwing a coin and then you get 2 children if it comes up heads, or you get 0 children if it comes up tails. So here we got heads, tails, etc. Right? So at first this, so what I need to say now is I kind of specified the dynamics of each individual, the reproduction dynamics of each individual, but I'm going to assume that all individuals are independent. So it doesn't matter if your neighbor gets 2 children, you are going to take your decision independently using your own coin. Okay, so this is one instance of this random family tree that we get. So here the population started to grow, sometimes it even doubled because everybody had children. And then at the end, just as the population suddenly doubled because everybody had children, descendants, here the population kind of drastically decreased because, they got a lot of bad luck. Until, at this generation, nobody reproduced, and then the population became extinct. So, in this particular model, what Galton and Watson proved was that extinction happens with probability 1. So, no matter how you toss the coins, since it's a 1/2 probability to get 2 children, the 1/2 probability to get 0 children, if you go on long enough and analyze this family tree long enough, eventually the population will become extinct. So their analysis of extinction used what's called a generating function. So here's the model. It's totally rigorous if you know what independence means. And so the quantities that we will be interested in is, for example, z of n, the size of the nth generation. So here I put, this gray squares kind of give you an idea of the size of each successive generation. And so that's zn, and we're going to use the generating function of what's called the offspring distribution. So mu of k will be now the probability to have k children. So we construct this generating function. It has a graph that looks a bit like this. So it ends at 1. It starts at mu of 0, which is the probability of having 0 children. And it is convex. And so there's what Galton and Watson proved was that if one is interested in rho, the probability of extinction, of eventual extinction, then this rho is the smallest fixed point of f. So here I put the identity, here's our generating function, and you see here the smallest root is 1, meaning that extinction happens with probability 1, and here the smallest fixed point is actually less than 1, meaning that there's positive probability that this population will survive forever. So what determines the two types of functions? Well, what determines them is the mean offspring, which is this sum of k times the probability of getting k children. If this offspring is greater to 1, then the generating function looks like this, or in this supercritical case. Whereas if rho is less than or equal to 1, then we are sure that we will become extinct, right? So that's the strategy to follow if you want, your favorite mathematical branch to survive. Just make sure that on average everybody has more than one student, right? Good. So now that I've talked about supercritical reproduction mechanisms or reproduction probabilities, there is the notion of a supercritical Galton-Watson tree. This is the Galton-Watson tree where we chose the offspring mean to be greater than 1, so that there's positive probability that the population survives forever. So here are the first 7 generations of a supercritical Galton-Watson tree, and we're going to divide the population into 2 types. We're going to consider the prolific individuals, which are those who have descendants in each generation, and the non-prolific individuals, which are all the rest. So what I did in this drawing is to color with black circles the prolific individuals. And you know, if you have a prolific individual, then it has to descend from another prolific individual and so on. So that gives us a kind of a partition of a population. Whereas prolific individuals can give rise to non-prolific descendants. So once we have these two types of individuals, we'll just are going to count the quantity of prolific individuals in successive generations, as well as the quantity of non-prolific individuals. What one can prove is that this process that counts prolific individuals is a Galton-Watson process again, so it has kind of the same dynamics as Z, except that its reproduction law will be different. So I have to tell you what's the probability that Z1 of 1 has K children. And instead of telling you all the sequence of those probabilities, I'll just write what the generating function is. So what that is, you know, we're going to put a new axis at this point, which was the smallest root. We're going to scale it so that it's 0, 1, 0, 1. And this part is going to be the new generating function for the prolific individuals. In the same way, one can prove that if we consider the coupled process Z1, Z2, then this is a two-type Galton-Watson process. So what's this two-type Galton-Watson process? Well, it's the same, except that there's two dynamics. If you're, for example, an individual of the prolific type, then you have a certain probability, say, mu1 of K1, K2, to have K1 prolific individuals and K2 non-prolific individuals, whereas you have only a certain probability, mu2 of K, that a non-prolific individuals will have K non-prolific descendants. So that's a two-type Galton-Watson process. So more than just the generation counting process, I will be interested in the whole tree. So remember that a tree in combinatorics is just a graph which is connected and has no cycles. So here's the graph. Well, here we have three examples of graphs here. They have these vertices, which are the dots, and the vertices are joined by lines, which we call edges. And so here, for example, if we want to go from V1 to V4, we can do it through V2 and V3, or through V5 and V4. So there's two ways in which I can go from V1 to V4, and those two ways form a cycle. So in the second graph, we also have cycles, whereas in the third graph, which is actually a tree, we have no cycles. So any graph can be thought of as a metric space. So if, for example, if I want to compute the distance between this point and this other point, what I could do is to define it as the length of the path, or of the shortest path in the graph setting, that takes me from one point to the other. So here it's 1, 2, 3, and 4. Right? So, and that is useful in order to abstract the notion of a tree to a more analytical setting. And that is done through the concept of a real tree. So what's a real tree? It's going to be almost the same definition as a combinatorial tree. So it's a metric space, which is complete. That is a technical hypothesis. And now we go back to the analogy with the discrete situation. It is pathwise connected and has no cycles. So what is this? Well, pathwise connected, of course, we understand. But what is this property of having no cycles? Well, if we have two functions, phi1 and phi2, which are defined on whichever intervals you choose, and which take values on the tree, and which are continuous and injective, so that they're kind of a path that doesn't backtrack, and they start at the same point on the tree and end at the same point on the tree, then actually they go through all the same points. Right? That is kind of the notion of not having cycles on a metric space. And so a real tree is just a metric space, which is complete, pathways connected, and without cycles. So I'd like to represent trees like this, you know, wiggly lines, which of course have no cycles. To make useful models of trees, we need another way of understanding these real trees, and that will be done through functions. So this is this construction that I wanted to talk about. It is the tree coded by what probabilists call a Cadillac function. So Cadillac, I'll write it down, is French for one continues with the limits. And again, it's the kind of random function that we encounter all over probability these days. So here's one such example. This one is piecewise linear, except for the jumps that it has here and that I drew with vertical lines. So this is a very kind of simple function. Or we could have this kind of horribly looking function. What we're going to ask of this function, which we call x, is that it's defined on a certain interval 0 zeta. We don't care too much about that, but it's a finite compact interval, and that it takes non-negative values. We're also going to assume that it ends at 0 and that it has non-negative jumps. So what's a jump? A jump is the difference between the value of the function at t and its left limit at t. So these solid lines are the jumps. Those vertical lines are the jumps. Well, now I'll explain a procedure to construct a tree out of such a function. And that procedure goes through defining this pseudo distance. So I'm going to define the distance that depends on the function. And that t1, t2, it will be given by evaluate your function at t1, sum whatever, sum the value of the function at t2, and subtract twice the minimum value you see of the trajectory in the interval t1, t2. In fact, that's a pseudo distance. And with that, you can define an equivalence relation and just pass to the quotient space. So that's a formal description of the procedure that takes a Cadillac function with these properties into a metric space that is a real tree. But of course, it's not telling. So what's the intuitive idea behind this construction? So imagine you put glue underneath this, and then you just fold it, right? So this part will be glued to that part, and if you continue going down, you'll see that this part of the trajectory is glued to that, right? So we have a function a bit like this. You see, this will be joined to that, this will be joined to that, and at some point, you reach this local minima, where these 3 points will be joined, right? This one was joined to that one. So there's kind of an interval here, another interval here, and another one here. So what you get out of this gluing and folding and construction is kind of a tree that looks like this. And that's how one can construct a tree out of this kind of function. And of course, if I just said that local minima are branch points, then you can imagine that this kind of function in which the local minima are actually dense is going to give rise to a very complicated tree. Funnily enough, the local maxima give rise to leaves in a tree. So a leaf in a tree is a point such that when you remove it, you don't disconnect the tree. Those in this kind of random function will also be dense. So these are, so now I've explained the notion of a real tree. One possible construction of a real tree out of a Cadillac function. And now what I'm going to do is substitute this Cadillac function for random functions. So in order to get random real trees. So this is a simulation done by a PhD student here. It's one of the trees that we will be interested in. It has many nodes. And as you can see, it also has these kind of hubs. So these are individuals which have just a huge number of offspring. So these are the types of trees that we'll be interested in, and those are the trees that are associated to Lévy processes. So in order to introduce these Lévy processes, let me do something simple. I'll consider this genealogical tree, and I'm going to label it in a very special fashion. It's called a breadth-first fashion, giving rise to breadth-first walks and breadth-first labelings and breadth-first whatever you want. So what is this breadth-first labeling? So I start with the first individual and give it the number 1. Then I go through its offspring and give it successive numbers, 2, 3, 4, etc. Then I go through the offspring of the offspring and then again assign them successive labels in such a way that, for example, so 5 comes before 7, so all the labels that I give to the descendants of 5 have to be less than the labels I give to the descendants of 7. So that's basically the rule that specifies breadth first labeling. So now that we have the tree with these labels, I'm going to define the breadth first walk. So that's going to be defined through its increments. So I'm going to let delta x of I be the quantity of children of individual I minus 1. You'll see the minus 1 appear in a bit. Just bear with me for a while. We're going to define also x of 0 equal to 0, and of course x of I is just going to be the sum of the increments delta x1 up to delta xi. So for example, in this tree, you see that delta x1 is equal to 2, delta x2 is minus 1, delta x3 is 2, delta x4 is minus 1, etc. So I wrote them up here. And now the breadth first walk is obtained by starting at 0 and summing up these values as they appear. So we get this, and we get this kind of wiggly function that's to your right. So these functions are called either Lukashevich paths or just the breadth first walks, and they satisfy the following. They have jumps of size greater than minus 1. They are non-negative until we reach the last value, which is equal to minus 1. So we call these kinds of paths excursions. So they start at 0 and at the end at minus 1, remaining above 0 during the whole trajectory. So I'm going to explain a very nice relationship between the sequence of generation sizes in the tree, which is what I initially told you that I was going to be interested in, and the breadth first walk on the tree. So again, we'll let chi of I be the quantity of children of individual I. So this is like our delta xi, except that it has a plus 1. It doesn't have the minus 1. And suppose we want to count the number of individuals up to generation n. Right? So this is 1 at generation 0, 4, 7, 11, etc. So all individuals up to generation n either are, well, the initial individual or descend from somebody up to generation n minus 1, right? So if I will count all of the individuals up to generation n, if I sum all of the offspring of individuals up to generation n minus 1 and the initial individuals. So we're not really interested in Cn, but rather in the differences, Cn minus 1, which give us the successive generation sizes. So I'm going to subtract Cn from this bit, and I could just do it by subtracting 1 from each one of the chi's. And that's where the minus 1 from the last slide comes in. So I did the subtraction here, and what I get is that the quantity of individuals at generation n is equal to the quantity of initial individuals plus the breadth first walk at time Cn minus 1. So this gives us a recursive procedure to compute from the breadth first walk the sequence of generation sizes. And just to give you a taste of what's coming afterwards, if we did this in continuous time, the analog of this would be a differential equation that would be written like this. So x would be kind of like the continuum analog of a breadth first walk. This would be the cumulative population, and this would be the, generation sizes. So in the case of Galton-Watson processes, so I'm interested in the sequence of generation sizes, and what I just said was that you would obtain them by summing up, by constructing this breadth first walk, which is a sum of, the quantity of offspring that individuals have. But what we said at the beginning was that these quantities of offspring are independent random variables. So what I'm saying is that this x of n is going to be the sum of n independent and identically distributed random variables, so that xn becomes what's known as a random walk. Good. So one thing that comes out from all of this analysis that we've just made is that if I start with a random walk and solve this stochastic recursion, I would end up with a Galton-Watson process. And this is just a picture of what it could look like. So here I drew a tree, then I have the breadth first walk, and then solving this recursion, I get the sequence of generation sizes, which is, as should be, 1, 3, 1, 3, 3, 2, 1. So that's correct. And we're good. So let me now go back to the tree setting. But before that, I have to tell you how to do this with continuous parameters stochastic processes. So again, I told you that a random walk is just the sum of independent and identically distributed random variables. But when they come from trees, they're very special in that all of these increments are greater than or equal to -1. So they're a very special kind of random walks. They're called skip-free to the left, or just skip-free. And one thing one could do with these walks is kind of to construct a continuous time stochastic process is to scale them. You see, I can run the random walk for n steps, but do it in 1 unit of time. And then if I just try to do that on the computer, it won't be able to graph anything because xn might just grow too much. So what I need is to do some scaling, and it turns out that this is the correct scaling for many offspring distributions. And this is what's called the scaling of the random walk. A scaling limit is a limit of this. So this is kind of a random wiggly function, right? And I can take the limit as n goes to infinity to obtain something. And that something is called, well, in this case, Brownian motion, or in the more general case of having not only one random walk, but actually a sequence of random walks, I would get any possible Lévy process that has no negative jumps. So at this point, I think we need some pictures because probably nobody has seen a Lévy process before, right? Oh, I see some people lying, huh? Good, so let's put some pictures of Lévy processes. So here's one. We have to wait till it stops. So I showed you approximations to a Lévy process, and that's just what these approximations converge to. So that's these kind of wiggly random functions with discontinuities all over the place. So you might think that they're very complicated because the offspring, so that the distribution of these random variables is just completely general, right? So you might think that there's no hope of describing all Lévy processes, but actually you can describe them. You can describe them in terms of what's called the Laplace exponent. So we have completely determined all the possible Laplace exponents that can appear, and I'll show you the formula afterwards. But what I want to say here is that this Laplace exponent is very similar to the generating function of Galton-Watson processes that I showed you before, in the sense that it's convex, and it might look a bit like this, and that we're also going to be very interested in the greatest root now of this convex function. We'll get to that, hopefully. Just as I did scaling, no, I won't. Just as we did scaling limits for random walks, one could do scaling limits for Galton-Watson processes. So these scaling limits are now very easy to obtain once we know that there's scaling limits for the random walks. Why? Because we have a way of constructing the Galton-Watson process out of the random walk by solving this recursion. So what comes out of that analysis is that the scaling limits of Galton-Watson processes are called, well, we call them continuous branching processes, or name, and they solve this random ordinary differential equation. So why did I call it a random differential equation? Well, because this is a random function, right? Once you fix that function, then you just have a differential equation to solve. Except that it's a very complicated kind of differential equation, because remember that for most Lévy processes, the set of discontinuities is dense, right? So it's a really discontinuous function. So you might think that there's no hope ever of solving this equation, but it turns out that, well that's what we did here. And yes, one can not only show that solutions exist and are unique under some conditions, but also that if you apply, the most naive method you can think of for solving a differential equation, and that would be Euler's method, right? It converges. Right? Even though this has a dense set of discontinuities. So these continuous branching processes are also kind of determined by a Laplace type exponent, except that now the dependence on t is very complicated, and this Laplace exponent solves another differential equation where you see the Laplace exponent of the Lévy process appear, right? So here's the Lévy process and the branching process. Here it's the Laplace exponent of the Lévy process, and here you have kind of the Laplace exponent of the branching process. So very well, we can now understand that there's kind of scaling limits for these Galton-Watson processes, and that might make us think that there are also limits for the random genealogical trees that we can build from Galton-Watson processes. So that is correct, and that was actually proved by Aldous in in a sequence of papers between 1991 and 1993. We call it the Continuum Random Tree trilogy. And so the statement of the result is as follows. You're going to fix a technical condition, don't read it, distribution for the offspring. You're going to assume that it is critical. It means that the population becomes extinct with probability 1. And that it has this finite variance condition. Don't worry too much about it. It's very generic, and interesting things happen when it's not satisfied. And you define now tau m to be a Galton-Watson tree, but you're going to force it to have n vertices, right? So you're going to, throw your dice and see your population evolve until you see one of those family trees that becomes extinct exactly when it has n individuals. So that's your Galton-Watson tree condition to have n vertices. And remember that I told you that you can think of a tree as a metric space. So here's the distance in that metric space. And what you're going to do is you're going to alter the distance by dividing it over the square root of the number of individuals. And now you're going to take a limit of this metric space. So there's a whole theory that tells you how to deal with limits of metric spaces, and so weak limits of random metric spaces. And that converges to a real tree, to a random real tree that has the name of Continuum Random Tree, or just CRT, and we typically call it Aldous CRT. So in order to get an idea of how this continuous random tree looks like, remember that we had this concept of the tree coded by a function, right? So we're going to code a tree by a random function, and it is this random function, which is called the normalized Brownian excursion. So the continuum random tree is the tree coded by the normalized Brownian excursion. And just so that you get an idea of how another Lévy process looks like, here's the normalized Brownian excursion, and we get it out of a process called Brownian motion, which is the one I wrote here, which is your prototypical continuous Lévy process. So it's a Lévy process which is not discontinuous all the time. So it looks a bit like this. And to construct the normalized Brownian excursion, you're going to fix a deterministic time. You know that Brownian motion is not going to be 0 at that deterministic time. So you define the last 0 and the first 0 before that deterministic time. So that gives you an interval at which Brownian motion is not 0. Now you take absolute value of that, and you kind of shift things a bit so that it's defined on 0, 1, and you have the correct spatial scaling, and that's called the normalized Brownian excursion. So, in summary, the normalized Brownian motion through the normalized Brownian excursion gives you access to the most famous continuum random tree, or random real tree. Now we're going to pass to a chronological model on trees. So this is a model called the splitting tree model. And in this model, time will be continuous. So now, what is a chronology and how it differs from a genealogy? Well, in a genealogy, we have no notion of time. You know, we have individuals and their offspring. They define the successive generations. But in chronologies, I have to specify, besides all these genealogical structure, what are the birth and the death times of each one of the individuals, and at what time do the offspring appear in the population. So our model considers this chronological aspects as follows. We're going to consider a population in which individuals live for a certain lifetime. It's going to be random, during which they reproduce, right? So here I represent the lifetimes as vertical segments. And so time flows upwards. And along these lifetimes, there's going to be moments at which the individual just reproduces. At each reproduction event, only one offspring will come to life, here. And this is done at constant rate throughout the whole lifetime. So yeah, a constant rate is a phrase that means, that is very clear for probabilists, but maybe it's not clear for the rest of the population. And it's hard to explain. So one way to explain it is to say that on any given interval, there will be a random number of individuals. And once I fix that random number, say it was equal to 3 for this, then I will place the birth times uniformly on this segment. 3 of them, right? Good, so that's at rate, okay, so and you know, the probability that case equals 3 depends on this lambda, which is the, oh no, that's constant rate b, right? So it depends on the birth rate. So we're going to assume, again, that the lifetimes of different individuals are just independent. So everything is independent of everything else in this population. So it gives rise to these kind of pictures where, you know, I have vertical lines representing lifetimes, and the horizontal dashed lines just give us a sense of descendants, right? So this individual, represented by its lifetime, descends from this other individual, right? Good. So one thing that's interesting about this model is that one has a genealogy and a chronology. So the genealogy, how do I get, for example, the generation of this individual? Well, I just need to see how many times I have to go through these dashed lines. So here there's 1, 2, and then 3. So the generation of this individual is 3. So there's a genealogy embedded in this model. Good. So, and since there's a genealogy, we have several notions of branching processes that we can consider. For example, we could consider the quantity of individuals that are alive at a given time t. So I fix a time t, and I just count how many individuals. So for example, here there's only 1, here there's 2, here there's like 5, etc. We could have another branching process, which is just the size of the nth generation, and that turns out to be, in this splitting tree model, a Galton-Watson process. And then there's a third one that I won't worry too much about. So there's a very particular case that's very dear to probabilists and nuclear scientists, and that's called the Yule process. And it is a model in which individuals just live forever. Why not? And so we have this first individual, lives forever, and at constant rate, you get its descendants. And now the first branching process, so that's the quantity of individuals alive at time t, It's what's called the Yule process, and one can make a whole bunch of explicit computations with this process. It's a very well-known stochastic process. But we're interested in the general ones, where this lifetime is random rather than deterministic, as in here. So using the Galton-Watson process that's embedded in this population model, one can actually deduce from the Galton-Watson analysis of extinction that these genealogical or chronological trees are finite almost surely if and only if this parameter m, which is equal to the birth rate times the mean lifetime, is either less than or to 1 in the subcritical case or equal to 1 in the critical case. In the supercritical case, there is positive probability that these trees will just be infinite. Will go on forever. So I'll explain now a way in which one can explore this tree in order to get a Lévy process, or a Lévy type process. So one is going to explore all the lifetimes of all the individuals, starting with the initial individual of the population. And lifetimes will be explored from top to bottom. So we start exploring the lifetime, and then suddenly we'll get interrupted by this birth event. And when we're interrupted by a birth event, we just go to the top of the lifetime of the individual that was born. So here we go again. We jump to the top of the lifetime, jump to the top of the lifetime, and then when we reach a moment where we haven't been interrupted and we reached a birth time, then we just go back to the lifetime of the parent where we left off. So that gives you a way of exploring the tree. And if you now record the time that you're exploring, so as you go doing this exploration on the tree, then you get a function. And the function looks a bit like these segments here. So let me erase first the genealogy that's that was on the tree. Then I'll erase the vertical jumps. And this is the type of function that you end up with. So it's a function, as in the beginning, that starts at that is non-negative. It has only positive jumps, because I always jump to the top of the lifetime, and it ends at 0. So it codes a tree. And the thing is, the tree coded by this function is exactly giving us all of the information of the chronology in the model that we introduced. So what Lambert proved in 2010 was that in the subcritical case, this random function, which is called the contour of the tree, is a special type of Lévy process. So it's a non-crazy type of Lévy process in which actually it's piecewise linear, and it doesn't have dense jumps. It's a very nice controlled process. So these are called compound Poisson processes, and they're completely specified by their jump distribution and jump rate and whatnot. Except that, this kind of Lévy process, you would just be able to let it go on forever, but to get a tree, we need to stop it at the time at which it first reaches 0, which is over here. So I've kind of done the reverse procedure. So I had a chronological model on trees and then constructed random processes with that. And the question that we had in our joint work with Amory Lambert was how one would be able to obtain not only these types of very simple Lévy processes, but Brownian motion or stable processes, or those really crazy types of Lévy processes. However, Lambert also had another result that was also a motivation for us, and that is that in the supercritical case, so for example in the Yule tree case, the contour of a splitting tree, well, it's no longer defined. We needed a finite tree to be able to do the contour, to be able to jump to the top of the lifetime. And the way to associate a contour to these kind of infinite trees is to choose a truncation time. So I just chose it here. Call it R if you want. And then forget everything that happens after time r, and that gives you a now finite tree to which you can associate a contour that looks a bit like that. And what Lambert proved now is that in the supercritical case, the contour of a splitting tree truncated at height r is another compound Poisson process, but now it's going to be reflected. So reflection in this setting can be constructed as follows. So we have a function here, x, this is our Lévy process, r, so it starts at a positive value, goes crazy for a while, and then, well, the typical Lévy process will go above height r, and then maybe 0. And what we're going to do to reflect it is to erase all of the bits of the trajectory that are above level r. We do this through what's called the techniques of time change, and done by defining first AT of r to be the quantity of time that the process has spent above time r. And then, you know, this is a continuous non-decreasing function, which might have intervals of constancy or whatnot. And what we're going to do now is to construct what's called the generalized inverse, which just needs you to, you know, shift your head and see this as a function now defined on this interval. And whenever you see an interval of constancy, it means that this function jumped. And then we define x of r to be x of c of r. And that effectively removes all of these parts of the trajectory where the process is above level r. So that's how you construct a Lévy process reflected below level r. So that gives us access to supercritical splitting trees and Lévy processes. Good. So now I'm going to tell you how to do all of these things with a general Lévy process, and that goes through the excursion measure, which I'm going to define right now. So remember that Lévy processes are characterized by their Laplace exponent, and now I have written the formula of what they look like. So it's basically a very simple function plus a totally inaccessible one. You see, so here you have some quadratic terms, linear terms, and, you know, independent terms, and here you have a measure. And this measure is telling you how your process, your Lévy process will jump. So if this is an infinite measure, your Lévy process will just jump all the time. It will have dense jumps. Whereas if this is 0, then your Lévy process will be continuous, and it'll be basically a Brownian motion with drift and kilt at a certain rate. So now with any Lévy process that might look a bit like this, I'm going to define the reflected Lévy process. How? By first constructing the cumulative minimum process. So here's the cumulative minimum. You see this, you know, I'm constructing the minimum as I go along, the minimum value I've observed as I go along. And then I'm going to subtract the value of the process from this cumulative minimum. So that looks like that. And then we change it. And this is out of the original Lévy process that I had, I constructed a new Markov process that looks a bit like this. Good, so that's the reflected Lévy process. And now I'm going to construct its excursion measure. Well, this is a very kind of complicated type of random process because it kind of has these excursions above level 0, except that one thing I haven't told you about is that if you consider the set of times such that this reflected process is at 0, then, and you close it, then this is a perfect set. So, yeah, this is one way in which probabilists like to construct random perfect sets, using the 0 set of their favorite stochastic process. What that means in terms of these excursions is that they're not like clearly delineated, as I said here. There's no next excursion, right? Between any two excursions, there'll be an infinite number of excursions, right? So we can order them. And so one way in which we have found a way to study them is through what's called the excursion measure. And that's just simply a sigma finite measure, mu, such that if we consider for this process only the excursions of length greater than epsilon n, there's only a finite number of them on any compact interval. Their distribution, we call them mu of n. Then this measure mu encodes all the measures mu of n. So this measure mu is a sigma finite measure on trajectories that are of the excursion type. So they start at 0 typically, they might start at a non-negative value and end at 0. So it's the kind of functions that we love for constructing trees. And so in the case where our Lévy process x is subcritical, and that means this function here has b equals 0, then we will associate to it a random real tree that is the tree coded by x under the excursion measure m. And that's one way in which we can associate to any Lévy process these random trees, random real trees. So, this, you don't really need to look at it. Do you? No. Oh, well, yes, because I have to tell you how you do this construction in the supercritical case, and that's actually a bit complicated. So what in your supercritical case, the thing is that your stochastic process x will go to infinity, and so there's one excursion of infinite length, right? So the excursion measure can actually be decomposed as its action on finite excursions and its action on infinite excursions. And the infinite excursion bit here, this is a probability measure that is equal to the law of the post-minimum process of your Lévy process. So that's what the excursion measure is. But we need something else in order to be able to construct a locally compact real tree, and that is a sequence actually of compatible excursion measures. So I'll just briefly go through that. So let me tell you how you can construct locally compact, forget the Tom thing here, locally compact trees out of now sequences of functions. So imagine you had a tree. It's locally compact, it's infinite. But you truncate it at level r, so it's now a compact tree. It has a contour, that's f of r. And these contours are, well, okay, so either the trees are compatible under truncation or the functions are compatible under time changes. And we say that that happens when, you fix your sequence of levels going to infinity at which you truncate, and then when you truncate at level r of n, the tree that was truncated at level rn plus 1, then it gives you back the tree truncated at level r of n. So if you have a sequence of trees that is compatible under truncation, then you can construct a unique locally compact tree such that truncating it at level r of n gives you your nth tree in the sequence. And that's how you construct a locally compact tree out of a sequence of compact trees. You can do that the same at the level of functions. So now I need to do that at the level of random functions. And that's what the next slide should be about. But it's not. So I'll just tell you how you construct it. You need to define a sequence of measures that is compatible under time change, and that's going to be the measures n of r, and they're going to be constructed as follows. So first, on compact trees, I just truncate them at level r, and to get the action on the locally compact part of tree space, then what I do is I'm going to define this new law, P right arrow R, which is constructed as follows. So first we'll have the post-minimum process of a Lévy process, time changed to remain below R, so reflected below level R. This will have a finite lifetime, so because the process will drift to infinity. And at this point, we're going to paste some other Lévy processes that are also reflected under time R, and which might also have a finite lifetime. And we're going to keep on doing that until one of these processes reaches 0. So this is now a function that's defined on trees that are truncated at level R. And one can prove that this sequence of functions is compatible under truncation, so that one can define a unique measure n on locally compact trees such that truncating the tree, the locally compact tree at level R, we get precisely this measure n of R. So that's how you construct locally compact trees associated to any Lévy process. But finally, I'm going to state a very, it's a nice theorem, but it's slightly technical. And it has to do with the genealogy that is encoded by these types of chronologies. So I'll just say then that for these types of trees that we just constructed, one can build a genealogical tree by a very complicated construction involving what probabilists call local time. So we can do that. That's what's said here. And then on this locally compact tree, now we have a locally compact tree, we have a notion of infinite lines of descent. So if you have a tree, an infinite line of descent will be an isometry from an infinite interval into your tree, right? So that's an infinite line of descent. And so here's, we represented a tree with infinite lines of descent and some compact trees that are grafted to this infinite line of descent. So under our measure on genealogical trees, one can define the process that counts the number of individuals that are sitting at an infinite line of descent at distance a from the root. So if this is distance a from the root, we'll see that here I think we have 5 infinite lines of descent, whereas here we have only 1 infinite line of descent. So this process turns out to be a Galton-Watson process. So we just came back to where we started. We can compute explicitly its jump distribution and jump rate. So this is these horrible looking expressions. But the thing to note about them is that they're completely determined by the same quantities that determine your Lévy process. And finally, that there's a version of the counting process for non-prolific individuals. And that, you know, counting process is not really a counting process. It's a rather Nicodim derivative, but don't worry about all that. There's a way to define this of measuring non-prolific individuals. And it turns out that, just as for supercritical Galton-Watson trees, the couple of process Z1 and Z2 is a 2-type branching process that can be completely specified, and I think I'll end with that. Beautiful formulae that completely specify this 2-type branching process in terms of 3 Lévy processes that govern the reproduction of prolific individuals, giving rise to prolific individuals, the reproduction of prolific individuals giving rise to non-prolific individuals, and the reproduction dynamics of non-prolific individuals. Thank you very much. He said thank you. Yes, so sorry, I probably compiled the wrong version of the bibliography. Just appeared.